So hi everyone, so nice to be here. So I'll talk about Byzantine Consensus, and we'll consider permission blockchains, but as hopefully will become clear, the basic principles would apply outside that domain as well. Right, so just a brief reminder, as basically everyone here knows at least something about this thing called blockchain or distributed ledger. So that can be viewed as process and abstraction. So there, this abstraction of append-only list of events. So this is a distributed ledger, and these events not necessarily just financial. So networks such as Ethereum, for example, allow arbitrary state machines to be implemented on top of them. And the important thing is that particular going to be our focus at this talk is that everyone has to agree on the content of the ledger. And the ledger must be tamper-proof. That means that not all parties are necessarily honest, and we need to have some protection in place to prevent dishonest parties from disrupting the ledger. So, for example, going back in time and messing up with some of the events that have been recorded. Okay, so what is a blockchain? So the blockchain is basically this magic that enables the abstraction of distributed ledger, and it is in essence a decentralized trust infrastructure. It is enabled by a network of nodes managing a chain of transaction blocks. So this is why we call it a blockchain. And the vision, of course, behind this decentralization is kind of an extreme libertarian democratization of finance, governance, decision-making, and many other things. Okay, so this is a quote from my former PhD advisor, Dalia Malhi, who is the chief scientist of Diem Association, is that the mission of Diem is to enable financial inclusion through an efficient and secure payment rails. So just notice this word's financial inclusion. Right. So so how blockchain looks like? So this is something like this. So we have these transactions that are actual events affecting the ledger structure. They are organized into blocks and they are chained together. So this is why it is a blockchain. And important property that everyone has to agree on content, as we discussed. Okay, so this is important because this prevents forks, right? And the forks in the blockchain can result in all kind of unpleasant things, such as, for example, double spending. Like you can see here, that if we have a fork, then a dishonest buyer, for example, can pay twice to different seller using the same coin. Right, so so this is without consensus on the left, and with consensus, of course, only one branch can win, and therefore these kind of scenarios will be prevented. Okay, so distributed agreement is something we are going to focus on. So distributed agreement is also known in the literature as consensus. And the specific flavor of consensus we are interested in is called Byzantine Consensus. And this problem is very simple to formulate. So we have multiple nodes, say in the blockchain network, that need to agree on a single value, right? So it is called a Byzantine Consensus because we typically assume a threshold, say F, of the total number of nodes n that can be compromised, can be dishonest in any way, and then they can try to actively subvert the network and fork the blockchain and do other kind of nasty things. So this threshold, so different types of blockchain consensus make different assumptions about this threshold. So Nakamoto, for example, assumes that this is less than 50%, and more kind of standard approaches to distributed consensus assume that this is less than a third of the network. So blockchain operates by repeatedly applying consensus to agree on a sequence of blocks in a ledger. So basically, the subject of consensus in the context of a blockchain, there are, say, multiple blocks that are competing to be the next block, say, block number 20 in the blockchain. And the idea is that consensus would guarantee that only one of these competing blocks is going to win and become the block number 20. Okay, so we will focus on permissioned ledgers in this talk. So permissioned ledgers, sometimes called the proof of membership ledgers or proof of authority, things like that. But the principles will be valid basically in all committee-based systems. And these include, among other things, Hyperledger, Libra, Tenderbake, Tendermint, Algorand, Ethereum 2.0, and so forth. Okay. So Byzantine Consensus also happens to be one of the most studied problems in distributed computing. However, classical protocols have been often criticized for their complexity, poor scalability, and performance, and apparently low practical value for this reason. So there was a famous, or I would say infamous, article by James Makins in Communications with the ACM in 2009, where he heavily criticized the current zeitgeist at the time for Byzantine Consensus. So he has this diagram where there are like multiple phases of voting that have been repeated in many papers, and it looks something ridiculous like that. And then he said that something that you can read here on the screen, that basically there's so much complexity and I don't understand why all of that is needed. But of course, you know, the time proved him wrong, and that Byzantine Consensus actually came into fashion after blockchain came to existence. And so people started thinking about how actually improve the classical protocols, and that led to a new wave of Byzantine Consensus protocols, and much of the development here was has been driven by industry. So here are some examples here. You can see, so these systems address many limitations of more classical approaches, such as the lower communication complexity, among other things, and many other new and interesting ideas. However, there's still a lot that remains to be unclear about this type of systems. So one thing is that they are difficult, so Byzantine Consensus is difficult to understand and reason about. So here's an example, so just so you believe me. So this is a pseudocode of the Tendermint consensus. So it's actually taken from the Tendermint white paper that was published some time ago. So you can see that this is kind of really, really complex. And in particular, what I want you to notice is that there are all kinds of conditions that basically has to do with synchronization and timeout management, which keep appearing in different places. And it's not really clear what they're trying to achieve, and what should be the timeout durations for things to work properly, and why we need these timeouts. right? So so that's one of the basic difficulties here, is that the protocol integrates inside some sort of synchronization mechanism that makes it really, really complicated. And as a result, it becomes quite complex to reason about the correctness, and in particular about what is called liveness. So liveness means that the protocol makes progress, right? And these synchronization mechanisms are needed precisely for that, to ensure that the progress is being made. So that led to bugs, and so these bugs have been reported in a number of papers. And just to give you some quotes, so this is a famous correct by construction Casper bug. It's definitely innovative, but the protocol is not live, even under very strong assumptions about the network. So this paper reported on both safety and liveness violation in various published consensus protocols. So this paper found bugs in Tendermint liveness protocol that we just discussed briefly. So this paper confirmed that bug and also reported another bug, which is in BFT raft. Okay, so so that's the situation, and basically the question we set out to ask ourselves when we looked at that, if we can do better. And we are a team of basically distributed systems and programming languages researchers, and that was kind of shameful, I think, that the situation was like that, and that you know, really very few people, if anyone, can clearly understand what's going on there. Okay, so that was the question: is if we can develop a framework for systematically designing correct Byzantine Consensus protocols, and if so, what are the right abstractions that can be used to make them modular, more easier to understand, easier to reason about, and so forth. Okay, so the basic observation that we made is that all existing consensus protocols exhibit a clearly identifiable epoch structure. Okay, so it will become clear, I hope, in a few moments what we mean by epoch. So these epochs are implicit in Nakamoto consensus, or they explicit in other protocols such as PBFT, Ouroboros, Definity, Hot Stuff, Tendermint, etc. And another follow-up observation is that consensus becomes much easier if all participants have a common notion of an epoch they're currently executing in. Okay, so if there is a situation, then what we can do is, for example, have a unique leader of an epoch, and that leader would enforce a decision which everyone will agree to. Or we can possibly, in addition to having a leader, we can have further rounds of voting if we want better protection, better finality, and things like that. Okay, so just this very, very simplified picture how it looks like. So that's say we take an example of Nakamoto consensus. So we have these epochs here. So we have someone who successfully mined the block, and that person kind of implicitly becomes a leader, and then can basically just propagate the correctly mined block to everyone. And if we kind of sparsed this, if you set up a proper complexity difficulty level for the puzzle, then we can also spread out these mining events so that they don't interfere with each other, right? So of course, oversimplifying greatly, but this is in essence what happens in Nakamoto consensus. So there are kind of epochs like that. So someone mines the block in an epoch, propagates the block, and everything is good. Okay. So so if we kind of agree with this intuition that if we have epoch structure, then consensus become easier, then the next question is how we can actually generate this epoch structure and capture its properties. So that was the problem we considered. So one simple solution one can think about is to use synchronized clocks, and synchronized clocks actually have been used in systems like Definity or Ouroboros, but again, synchronized clocks are difficult to achieve, especially at a large scale, and in the presence of timing faults and compromised nodes. So it's better not to rely on synchronized clocks. So another approach which we kind of considered is that integrating with the actual consensus code, but that results in very complex and bug-prone algorithms. Okay, so so the abstraction that we came up with is called View Synchronizer. Okay, so the basic ideas of distributed clock synchronization can still work. So this is what we kind of observed when we worked on this abstraction. But the goal of clock synchronization, which is minimizing skew, is a kind of a wrong objective, because it's doing much more than needs to be done to achieve what we need. And what we need is actually something that ensures that all participants overlap in the same view for sufficiently long when the network is timely. So with that, we can solve consensus. So just a quick note on terminology. So view is the same as epoch, is the same as round. So we'll see these things interchangeably. So we used views because the specific protocols we looked at were view-based protocols. Okay, so this is how it looks like on a diagram. So we have this view synchronized abstraction, and it exports a simple interface, which is a new view. And on top of that, we put a core consensus protocol. So basically what Synchronizer does, it tells nodes when to switch views. And turns out that this structure can be reused across many different protocols, and that leads to more systematic design. So here's the kind of just to illustrate Synchronizer specification. Well, I know I'm running low on time. So this is a kind of the actual picture that occurs in reality. So epochs, of course, don't need and can't be this nicely synchronized, as I have shown before on that picture. So in particular, there could be timing faults, and we want to tolerate timing faults, right? So the basic approach is that when there are timing faults, then views or epoch not necessarily synchronized, and as a result, consensus can be, the system may not be able to achieve consensus, but once we have a period when there are no timing faults, then Synchronizer will enable us to converge to more kind of structured view of the system. That could be done even in the presence of some Byzantine or dishonest nodes. Okay, so what is this more structured view of the system? So this is something like this. So these dotted lines here indicate the beginning of the views, right? So there's like views are consecutive. So not everyone necessarily enters the same view V at the same time, but what we have here, we have an overlap. So this green area shows the overlap. And if we can ensure that we can have this overlap of a proper size, proper means that it's enough time to solve consensus, then Synchroniser has achieved its goal. Okay, so that's the most important part of the Synchroniser specification. If you're interested, the paper below with colleagues gives the full formal specification of the properties. So in addition to that, we also kind of require this limited discrepancy at the entry into every view, and it turns out that some protocols actually require that. So for example, Tendermint requires this property that we can also bound the discrepancy in the entry time. Okay, and when system is timely, then this picture kind of continues to repeat itself, and then we can also set up Synchroniser in a way that this overlap keeps increasing. For example, if we don't know the network delay, things like that, and then eventually, if there is enough time when we don't have timing faults, and then consensus will be solved. Okay, so this is one of the simpler implementations of Synchroniser that I don't have time to discuss, unfortunately. So, so let me just say that Synchroniser can be implemented efficiently, and we don't even need to rely on expensive public key primitives. So that an example is a fast sync synchronizer in this paper. There are also other implementations that improve various concepts of view synchronization, such as Coxworth and this paper here, who looked at minimizing communication complexity, but at the expense of using threshold signatures. Okay, so we considered a number of case studies, and we actually been able to put a number of real consensus algorithms used in the real blockchain implementations into the Synchroniser framework, and as a result obtain very simple, very clear algorithm, almost didactically clear. So here are some examples of algorithms that we considered, and so this is one of well-known consensus algorithm, Byzantine consensus algorithm called PBFT, which is in that, which is expressed in that framework. And if you read the description, it is incredibly complex. But if you use Synchroniser, okay, this is the code you end up with. Okay, so I can teach it in an undergraduate class. It's not. It looks quite simple. Okay, so we came to a conclusion. The main point I want you to take away is that this abstraction of a view synchronizer puts Byzantine consensus protocols into a uniform framework. Synchronizer can be efficiently implemented, and it serves as a rigorous foundation for designing and comparing modern Byzantine consensus protocols. And we continue working on further exploring this direction, these directions, and we're currently looking on on-demand view synchronization, which is useful for protocols that apply consensus repeatedly. We also looking into generalizing synchronizer for probabilistic Byzantine consensus, such as Nakamoto, or for different connectivity assumptions about the network, and also other types of concurrent systems and algorithms.